This presentation on confidence intervals is part 2 of a series of presentations on statistical inference. The instructional design for this presentation was developed by David Kleinbaum, statistician, and Anna Washington, educator, and the narration was done by David Kleinbaum. In this presentation, we describe how to compute a confidence interval for the mean mu of a population. More specifically, this presentation shows how to use a sample, as shown below, to compute two numbers, seen here as L and U, which define a confidence interval. For such an interval, we can state with a specified amount of confidence, for example 95%, that the mean mu lies somewhere between L and U. Notice that this picture shows a 95% confidence interval which contains the unknown mean mu. There's always a chance that the interval computed from a particular sample will not contain mu, but if we have a 95% interval, that chance is only 5%. Before we start to discuss confidence intervals, recall that in going from the actual sample of X, shown at the bottom, to an estimate about the entire population of X, shown at the top, there is another distribution that needs to be considered, the one shown in the middle. This distribution is called the sampling distribution of X bar, and it describes the hypothetical distribution of sample means that could result if we kept drawing different samples from the population of X. Keep the distinctions between these three distributions in mind because we will be referring to them throughout the presentation. They will always be shown in these relative positions and in these colors: blue for the sample, purple for the distribution of the sample mean, and red for the population. We are now ready to show how to derive a confidence interval by reasoning our way through a realistic example. We take you now to the town of Angina, North Carolina. The town planners and board of aldermen are trying to decide where to locate new low-rent housing projects. To help them decide where to locate new housing projects, they have been studying the housing projects already in existence in Angina. One of the questions under study is the effect of racial composition of the surrounding neighborhood on the health of residents. Planners have undertaken a research study to measure the health of adult residents, most of whom are black, in projects where the surrounding neighborhoods are of varying racial compositions. One of the housing projects under study, as shown in the upper left of this screen, is Pine Knoll Community. Pine Knoll is about 98% black, yet the surrounding neighborhood is about 85% white. Of the 210 households in Pine Knoll, a random sample of 25 is selected to be interviewed about their health. A questionnaire measuring general health status is given to the 25 heads of household in the selected sample. It contains questions about previous illnesses and current signs and symptoms of illness. From the questionnaire, an overall health index of health status called the Cornell Medical Index, or CMI, is derived for each individual. This score can range between 0 and 100, where the higher the score, the poorer the health. It is the CMI score that is the variable X under study. In the top right corner of this picture are the CMI values obtained for each of the 25 heads of household in the sample. On the left is shown their histogram, with sample mean X bar and sample standard deviation S. Notice that the sample mean is about 20. A mean of 20 is on the lower, healthier end of the CMI scale. Still, whether or not this value actually indicates good health for those 25 people in our sample depends upon the health criterion of the clinician, and there must be interpreted relative to the health of other communities. Moreover, as shown below, we only have data from 25 heads of household, not from every head of household of the Pine Knoll population. As indicated above, mu, the true mean of CMI scores for all heads of household, might actually be higher or lower than the sample mean X bar. The distribution of CMI scores for Pine Knoll might in fact be one of many possible distributions, as pictured above, and we won't know which one unless we know mu. Moreover, since we are using a sample, we can never know mu exactly. However, we can use the sample mean X bar to estimate mu by means of a confidence interval. X bar and something else must go together to make up a confidence interval for mu. X bar is a good starting point for estimating mu, but using X bar alone is somewhat unreliable since its value varies from sample to sample. However, we can get a measure of the variability of X bar by looking at the sampling distribution of X bar. We can then take the variability into account along with X bar to obtain a confidence interval. The variability of X bar is customarily measured by its standard deviation, whose formula is given by sigma over the square root of n, where sigma denotes the population standard deviation of the variable x and n denotes the sample size. By the way, to distinguish the standard deviation of X bar from sigma, the standard deviation of x, we usually call sigma over the square root of n the standard error. Keep in mind that the standard error is the standard deviation of X bar, shown in purple, since you will be substituting it into formulas later. Now, since the formula for the standard error involves sigma, what value of sigma can we use to compute it? We will assume here that sigma equals 16 on the basis that we have obtained it as an average standard deviation of CMI scores from previous empirical research in various types of populations other than urban renewal projects. Although we are assuming here that sigma is known, more often than not in actual practice, sigma will be unknown. Therefore, it is of interest to consider how to compute a confidence interval when sigma is unknown, which involves the use of the sample standard deviation S. However, this will be discussed in the presentation to follow this one. With sigma assumed equal to 16 and n the sample size equal to 25, we can substitute in the standard error formula to obtain a standard error of 3.2. To restate the confidence interval problem for Pine Knoll, we are looking at a sample with mean of 20.84 and standard error of 3.2. We want to compute a confidence interval with limits L and U to get an interval estimate of the unknown population mean mu. Now, do we want a 90% confidence interval or some other percent? How much confidence do we want to have that the limits we are computing will actually cover the unknown mean mu? This question must be answered before we can find the limits of the interval. To decide on the level of confidence, we should know that the higher the confidence, the wider the interval. We need to weigh against each other the need to have the interval be wide enough to include mu, yet narrow enough to pinpoint mu in some reasonable way. For the Pine Knoll example, we'll choose a 95% confidence level. In practice, most investigators choose confidence levels between 90 and 99.9%, although there is no well-accepted rule for making such a choice. How can we use the sample mean of 20.84 and the standard error of 3.2 to derive a 95% confidence interval for mu. Intuitively, we could take the mean x bar and then add and subtract some multiple of the standard error to obtain upper and lower limits. Stated another way, we might find some number q such that the 95% confidence interval is of the form x bar plus or minus q times sigma over the square root of n. In fact, this is exactly the form that the confidence interval will finally take. However, let's put this intuitive formula on hold for now until after we show logically how this expression, particularly the value of q, may be obtained and where the 95% fits in. One of the properties required to derive the confidence interval is that the sampling distribution of x bar be normally distributed. This is a reasonable assumption for the pine knoll example, since a sample size of 25 is large enough for the central limit theorem to apply. In fact, even if the sample size were small, we could reasonably assume that x bar was normally distributed if the distribution of CMI scores had consistently been shown to be normal from previous empirical research. For it follows from statistical theory that x bar is normal if x is normal. Recall also that if mu denotes the mean of the x distribution, then mu is also the mean of the x bar distribution, even though the standard deviations differ and regardless of the normality assumption. Now, given that x bar has the normal distribution with mean mu, which is unknown, and standard error sigma over the square root of n, we can transform x bar to the standard normal or z-scale using the conversion formula shown in the arrow. That is, z is obtained by subtracting mu from x bar and then dividing the difference by the standard error. This formula is the familiar conversion formula for standardizing a normally distributed variable, although here the standard error sigma over the square root of n takes the place of the standard deviation sigma. In other words, the distribution of x bar on the left may be converted to the distribution on the right so that standard normal tables may be used to look up probabilities or determine percentiles. Keep this conversion formula in mind as we will be using it shortly to derive our confidence limits. The book illustrated on the top left gives information that may be found in a standard normal table like that in the appendix of your viewing study guide. Recall from using such a table that the probability is 0.975 that the value of z lies below 1.96. Alternatively, this means, as shown in the formula, that the middle 95% points of any z variable are minus 1.96 and 1.96. As a probability statement, this may be set up as the probability that z is between minus 1.96 and 1.96 equals 0.95. This statement will provide us with a mechanism for constructing the 95% confidence interval we seek. Now, starting with this probability statement about the middle 95% points of z, shown at the top, we can work towards our 95% confidence interval by first substituting for z the standardizing formula x bar minus mu divided by sigma over the square root of n. This substitution is shown on the second line. We can then further simplify this probability expression to the one at the bottom by substituting the values we have for x bar and sigma over the square root of n. The middle portion of the expression then reduces to 20.84 minus mu over 3.2. In the probability statement we have thus obtained, shown at the top, the only term that is now unknown is mu. Such an outcome is actually quite in line with our goal, which is to obtain an interval which will include mu. We can accomplish this by manipulating this expression mathematically until mu stands alone at the center, as shown below. And in fact, the limits we obtain will give the confidence interval we seek. The mathematical manipulations are as follows. Starting with the expression at the top, we first multiply each part of the expression inside the parentheses by 3.2, as noted on the left, to get an equivalent probability statement which has 20.84 minus mu at its center and minus 6.272 and plus 6.272 as its lower and upper limits respectively. Next, we must subtract 20.84 from each part of the expression to obtain the equivalent probability statement below, which has minus mu at its center and minus 27.112 and minus 14.568 as its lower and upper limits respectively. This statement is close to what we seek, but it is not exactly what we want, since we have minus mu in the center of the inequality rather than mu in the center. To get mu in the center, we next multiply each part of the inequality by minus 1, while at the same time reversing the inequality signs. Mathematical law requires reversing the direction of the inequality signs when multiplying by a negative number. The resulting expression now has mu in the center and says that the probability is 0.95 that mu is between 27.112 and 14.568. This expression is what we want, but it is written here in terms of greater than inequality signs. Since we started with less than inequality signs, the final step will be to rewrite it in that form. The final equivalent expression at the bottom has been obtained by both switching the numbers and reversing the inequality signs. It says that the probability is 0.95 that mu is between 14.568 and 27.112. From now on, we'll round these figures off to 14.6 and 27.1 for convenience. In summary, we have begun with a 95% probability statement about z, and using the standard conversion formula x bar minus mu divided by sigma over the square root of n, we have substituted values for x bar and sigma over the square root of n, mu being the only unknown term. After rewriting the expression several times, we have arrived at an equivalent interval with mu in the center. The 0.95 probability statement that we have obtained, which gives an interval for mu between 14.6 and 27.1, is called a 95% confidence interval for mu. We have thus completed the calculations for the Pine Knoll CMI data. Next, we will discuss how to interpret this confidence interval. What does this confidence interval say about the health of the population of Pine Knoll? For one thing, we can say with 95% confidence that the population mean CMI score for the heads of household in Pine Knoll is somewhere between 14.6 and 27.1. This population mean might in fact lie outside this interval, but because of the procedure by which we obtained the interval, there is only a 5% chance of this. We might also note that the interval obtained, which ranges between 14.6 and 27.1, is rather wide, making it difficult to pinpoint the health status of Pine Knoll residents. Nevertheless, if most clinicians were in agreement that a population mean has to be over 50, as shaded black, to conclude poor health for that population, then we could confidently conclude that Pine Knoll is a healthy community, because the entire confidence interval lies well below 50. On the other hand, if the clinician criterion for good health were 10 or under, as shaded green, we could be confident that pine knoll is not very healthy on the average. In other words, any decision on how healthy is pine knoll depends on one's criterion of good health. And if the criterion falls anywhere between 14.6 and 27.1, we cannot come to a firm conclusion. Further, we may want to compare pine knoll's average health, shown in the top scale, to other communities with different racial compositions in the surrounding neighborhoods, shown in the two scales at the center. Or we may want to compare pine knoll to a more general population like the entire country, shown at the bottom. When relative criteria can be specified, the extent to which conclusions can be drawn depends, as with absolute criteria, on whether or not the criterion lies inside or outside the confidence interval. Actually, the kinds of questions just discussed, in which a decision is sought about the pine knoll's average health, are in essence hypothesis testing questions. There is, in fact, a close relationship between a test of hypothesis and a confidence interval. We will not explore this concept further here. However, as we have seen, a confidence interval can be used to evaluate a hypothesis about a specified criterion in addition to estimating the value of a population mean. We've said just about all we can say about the health of pine knoll from the computed confidence interval. We will now use this interval to provide a short review of some more general properties of any confidence interval. In particular, notice that the probability statement for the interval, which has mu at its center, suggests that mu is a random variable. This, in fact, is not so. Mu does not vary at all, but rather is the single fixed value of a population parameter. Actually, the random elements of the interval are the limits 14.6 and 27.1, which are computed from the sample data and may vary from sample to sample. To illustrate further the random nature of confidence limits, observe these 10 95% confidence intervals that might have resulted from drawing 10 different samples of the same size from the pine knoll population. For this illustration, we are taking for granted that the true mean has been determined, and it is represented by the vertical red line. The confidence interval at the top is the one we previously computed with limits 14.6 and 27.1. Notice that the other intervals pictured all have confidence limits different from the first one. This is to be expected when going from one sample to another. Nevertheless, almost all the intervals share the common feature of including the population mean mu between its limits. The only interval out of the 10 illustrated which does not contain mu is the one highlighted. 9 out of 10 intervals which contain mu is about what we should expect if the intervals have a 95% confidence interval. More generally, we would expect 95% of all such intervals to include mu within their limits. We are now ready to get back to the general computing formula for any confidence level, which we put on hold a while back. We will proceed to describe this formula by working from the specific to the general. At this point, you may wish to take a break. Return to this presentation when you are ready to continue. The general formula for a 95% confidence interval for mu with sigma known is given at the top. X bar plus or minus 1.96 times sigma over the square root of n. This formula is a much more convenient way of computing the interval than starting with a probability statement about z as we did earlier. Applying this formula to the pine knoll example as shown below, we need only substitute the values x bar equal to 20.84, sigma equals 16, and n equal 25 to get 20.84 plus or minus 1.96 times 3.2. This simplifies to 20.84 plus or minus 6.272, which yields 14.568 and 27.112 as the confidence limits that we had found earlier. We now replace the 95% confidence interval formula given at the top with the formula for a 99% confidence interval, which is shown just below it. The only difference between the two is that 1.96 is now replaced by 2.576. The reason for this change is that we need to determine the middle 99% points of Z, shown at the bottom right, rather than the middle 95% points crossed out at the bottom left. From the standard normal tables, the middle 99% points of Z are minus 2.576 and plus 2.576. To obtain the 99% confidence interval, then, we simply substitute 2.576 in the confidence interval formula in place of 1.96. Suppose we compare pictorially the 95% confidence interval formula given at the top to the 99% confidence interval formula given at the bottom. Look at the respective widths of the intervals shown in the middle. Since 2.576 is larger than 1.96, the 99% confidence interval will be wider than the 95% interval. In fact, it is generally true that the higher the confidence we want, the wider must be the interval. To be more specific, here we compare the 95% and 99% confidence intervals obtained for the Pine Knoll data. The 95% confidence interval requires 6.272 to be added to and subtracted from 20.84, whereas the 99% interval requires 8.143 to be added to and subtracted from it. As seen in the middle, the resulting 99% confidence interval limits of 12.7 and 29.9 are wider than the 95% confidence limits of 14.6 and 27.1. The only difference between the 95% and the 99% intervals are the circled multipliers 1.96 and 2.576. Therefore, to compute a confidence interval other than 95 or 99%, we must find a different multiplier, which we have kept unspecified in the bottom circle. In order to give a general expression for this multiplier, we must first consider how to write a general expression for the confidence level, which is the unspecified percentage at the bottom left. We can fill in the blank percentage at the above left with the expression 100 times 1 minus alpha. This makes more sense if we notice below that 1 minus alpha is the area in the middle of the distribution curve, leaving alpha to represent the combined area in both tails, each with an area of 1/2 alpha. In order to use the expression 100 times 1 minus alpha to give a general form for the multiplier, which still remains blank for now, we need to find the middle percent points identified on the z-curve below. First, however, we need to determine the value of alpha. Given a specified value 100 times 1 minus alpha, it is a matter of simple arithmetic to solve for alpha. An example is given in the central panel. If 100 times 1 minus alpha is 95, in other words, we desire a 95% confidence interval, then 1 minus alpha equals 0.95 and alpha equals 1 minus 0.95 or 0.05. In the right panel, this example is pictured. Alpha is the combined area in both left and right tails, the area in each tail being 1/2 alpha. Having denoted the confidence level in general as 100 times 1 minus alpha at the top left, we can now write the multiplier we seek in terms of alpha. This multiplier is written as z sub 1 minus alpha over 2, since the area under the curve to the left of this point is 1 minus alpha over 2. Notice in the picture below that the multiplier can be obtained by finding the middle 101 minus alpha percent points of the z-curve. With 1 minus alpha of the area lying in the middle of this curve, alpha over 2 of the area must be in both the right and left tails. Thus, the upper percentage point that is pictured is z sub 1 minus alpha over 2, since the area under the curve to the left of this point is alpha over 2 plus 1 minus alpha, or 1 minus alpha over 2. This multiplier and its point on the z-curve is shown again in the upper left, and an example is worked on the right. Suppose alpha equals 0.05, then alpha over 2 equals 0.025, and 1 minus alpha over 2 equals 0.975. So the point on the z-curve to be looked up in the table is 0.975. The resulting multiplier found in the table is 1.96. Notice from the illustration that z sub 0.975 percentage point is one of the two middle 95 percentage points of the z distribution. That is the one in the upper tail. So the general formula for computing a 101 minus alpha percent confidence interval for mu when sigma is known is x bar plus or minus z sub 1 minus alpha over 2 times sigma over the square root of n, where x bar denotes the sample mean, z sub 1 minus alpha over 2 is the 100th times 1 minus alpha over 2 percentage point of the z distribution, and sigma is the population standard deviation of x. To review the entire computation procedure for the confidence interval, we will use it in a second example. A special reading program is being tried out with 6th graders in a particular school system. Concurrently, a study is undertaken on a sample of them to measure the amount of improvement in reading ability. For each 6th grader, in a sample of 49, a standardized reading test is given prior to and following a 2-month period of the new reading program. The difference between after and before test scores is then used as a measure of improvement per learner. The question under study, therefore, is what would the improvement be for all 6th graders if the program were adopted for all schools in the system? The variable x being studied for this reading program is thus the difference between after and before test scores for each learner. Our confidence interval problem is to estimate the population mean mu for the distribution of the difference scores represented by the variable x. Notice that although x is actually the difference between two variables, our problem involves a single variable, since we are focusing on the combined difference score, which measures improvement. Suppose that for the sample of 49 6th graders, the sample mean of improvement scores is 6.5, and suppose also that it can reasonably be assumed from studies of this reading program in other systems that the standard deviation of improvement scores is 4.2. What is the 90th percent confidence interval for mu, and how can it be used to evaluate whether significant improvement in reading ability is being made? To solve the problem, we use the general formula which is given at the top. To do this, we first find the value of the multiplier z sub 1 minus alpha over 2. Since our confidence level is 90%, we can find alpha by solving the equation 100 times 1 minus alpha equal 90. Using algebra, 1 minus alpha equal 0.90, so that alpha equals 0.10. Therefore, alpha over 2 equals 0.05, and 1 minus alpha over 2 equals 0.95. So we need to get z sub 0.95, the 95% point of the z-distribution, whose value in the table is 1.645. Notice that the area under the z-curve between minus 1.645 and 1.645 is 0.90. With the multiplier now determined to be 1.645 substituted in the general formula, we can further substitute the other values to solve the problem. X bar equals 6.5, sigma equals 4.2, and n equals 49. Thus we have 6.5 plus or minus 0.987, which gives 90% confidence limits of 5.513 and 7.487. For interpretation purposes, we will round off these limits to 5.5 and 7.5. Thus, we are 90% confident that mu, the mean improvement score in reading ability for all 6th graders in the school system, is somewhere between 5.5 and 7.5, although there is a 10% chance that mu is outside this interval. In using this interval to evaluate whether significant improvement has been made, we first notice that both limits are positive and that the interval does not contain 0. Thus, we are at least 90% confident that some positive improvement has been made. In addition, we might like to decide whether the improvement made was sufficient to be called a success. To make such a decision, some criterion must be used. For example, let's suppose that educational research or theory indicates that an improvement score of 10 or more on this test is required to make any reading program a meaningful success. Then we would have to conclude that our program was not a success, since we can be 90% confident that the mean lies below 10. On the other hand, if an average improvement score of at least 7 is the criterion, we cannot state with confidence that the program is either a success or a failure, since the interval's limits lie both above and below 7. Nevertheless, we can say with 90% confidence that the population mean improvement may be as high as 7.5. So we should not rule out the likelihood that the program might be a success. This concludes the second example. Here, for one last time, is the general computational formula for mu with sigma known. Since this presentation is almost finished, remember this formula as you proceed to the viewing study guide to work the practice problem and complete the test as a self-check of your learning. And now here's the practice problem, which is repeated in the viewing study guide so that you can have sufficient time to work it out. An authoritative person is defined as someone who is fond of giving orders, who likes to exert authority, or is dictatorial. Suppose a 20-point scale is derived from a questionnaire to measure this trait, with a high score indicating a more authoritative individual. Your problem is to find and interpret a 98% confidence interval for a population mean based on administering the questionnaire to a sample of social workers. This concludes this presentation. We suggest that you try the practice problem and check your answers. Then work through the test given in the viewing study guide that accompanies this program. You will then be ready to go on to the next topic, entitled Finding Confidence Intervals for mu when sigma is unknown.